Good afternoon, students and colleagues. Welcome to join Innovating to TechTalk. Today we are happy to have Dr. Zhao, Assistant Professor of Department of Urban Planning and Design from Faculty of Architecture, to be our moderator. Without further ado, Dr. Zhao, please.
Thank you. Can you hear me okay? Good afternoon, everyone. So welcome to Tech Talk. My name is Dr. Zhao. I'm currently assistant professor at the Department of Urban Planning and Design under the Faculty of Architecture. So I'm happy to chair this session. So this session is a part of the Tech Talk series, right? So Tech Talk is a series of forums and dialogues given by engineering researchers of diverse academic backgrounds to share their insights on innovation-related topics, right? So if you check your email, you will see some of the announcements for future events. So today is our great pleasure to have Dr. Jintao Ke to talk about his work on the simulation, optimization, and artificial intelligence for on-demand ride service operations. Before that, maybe I'll just start with some brief introduction for Dr. Ke. Dr. Ke currently is an assistant professor in the Department of Civil Engineering at the Hong Kong U. He got his PhD from Hong Kong University of Science and Technology, supervised by Professor Hai Yang, right? So it's a very famous figure in this field. His current research interests include shared mobility on demand, transportation big data analytics, multimodal intelligent transportation system, transportation pricing, and short-term travel demand forecasting. The vision of his research is to develop novel models, algorithms, and conduct data-driven quantitative analysis to better manage, operate, and regulate shared mobility and other emerging mobility services, which is very relevant for with today's topic. So he also published numerous papers. So I won't list them all, too many to name, right? So please also check his profiles on the department website and also Google Scholar to know more about his work. So without further ado, maybe I'll turn the floor to Dr. Ke to share his talk.
Okay, sure. First I thank Faculty of Engineering for organizing this activity, and also thank Dr. Zhao for introducing me. So today it is my great pleasure to be here to share some of my research with you. So the topic I'm going to introduce today is about a large-scale simulation platform for on-demand ride service operations and some related AI algorithms. So first of all, I will talk about the background and motivations. In transportation or in the field of smart mobility, there are majorly three trends. One is electrification. Now we can see that there are more and more electric vehicles on the roads. And the second trend is the shared mobility. That means we use one vehicle to travel multiple passengers. We use some private cars like Uber and Didi to travel to satisfy these on-demand passenger needs. And the third trend is automation, which means some autonomous vehicles. Nowadays, we can see that there's some tech companies like Tesla are developing some autonomous vehicles. So my research majorly focused on the shared mobility. So about the shared mobility, there are different modes. The first one is the ride sourcing, like Uber and Didi. There are also some car sharing companies and bike sharing companies. Take the ride sourcing services as an example. There are so many ride sourcing service providers, such as Uber and Lyft in US, and Didi in China, Grab in Southeast Asia, Ola in Middle East, etc. And these companies have experienced great growth in the past 10 years. For example, Uber has completed over 20 billion trips in over 80 countries and 700 cities. And Didi Suxing, as the largest ride-hailing company in China, is now serving over 20 million trips in each day. So for these ride sourcing services, there are many operational challenges and some interesting research questions. First of all, the platforms want to know how can we estimate the passenger demand and driver supply in the real time. And based on this information, they would like to match the drivers with passengers in the real time. And they want to set the price for passengers. For example, they can use dynamic pricing to adjust the price according to the real-time supply and demand information. And on the driver side, they want to set the wages for drivers. Also, they can also dynamically adjust the wage for drivers according to different situations. Another question is, how can we relocate the idle vehicles? We know that there are so many idle vehicles cruising on the street to find the next passenger. So the platforms may design some strategies to relocate those idle vehicles from one place to another to balance the supply and demand over the space and over the time. And from the perspective of the government wants to do some regulations to control the decisions of the ride-hailing platforms. They are interested in how can we understand the social impacts of ride sourcing services on traffic congestion, traffic emission, and public transportation usage. And based on this understanding, they would like to develop some regulations to enhance the social welfare to avoid the ride-hailing platforms only focusing on their own benefits, but ignore the benefits of others, like the customers, drivers, and other people driving on the roads. So to answer these questions, we first need to have a brief understanding of a ride sourcing system. A ride sourcing system is similar to a taxi system. It is a two-sided market with a platform in the middle and with passengers and drivers on both sides. On the passenger side, the passenger demand, namely the number of passengers who are willing to use the ride-hailing services, is first determined by the price set by the platform. When the price increases, then the demand will decrease, right? And it is also affected by the expected waiting time of passengers. When the passengers expect that the waiting time will be longer, then the passenger demand will also decrease. And on the driver side, the driver supply, namely the number of drivers who are willing to join the ride-hailing platforms to provide services, is affected by the wage set by the platform. When the wage increases, then more drivers are willing to join the platform. And it is also affected by the vehicle's utilization. What does it mean? We know drivers can only earn their profits when their vehicles are occupied by passengers, right? When they are idle, they cannot earn anything, right? So the vehicle's utilization, namely the proportion of time that is occupied by passengers, this is called the vehicle's utilization. When this utilization is higher, then the drivers would receive higher profits per hour or per day, so that more drivers will join the platform. In addition, the platform can also control the on-demand matching strategies that can match the passengers with drivers. And these matching strategies will affect both the demand side and supply side by affecting passengers' waiting time as well as vehicles' utilization. In addition, the passenger demand will also affect the driver supply by affecting vehicles' utilization. And in turn, the driver supply will also influence the passenger demand by affecting passengers' waiting time. So you can see that this ride-hailing system is quite complicated. It has so many variables that are interacting with each other. And the platform can control the price for passengers, the wage for drivers, and the on-demand matching strategies to achieve multiple objectives. For example, they want to improve the platform profit, and under regulations, they may also want to enhance the social welfare. And outside this system, the government can impose some regulations to control the decisions of the ride-hailing platforms so that they can focus more on the social welfare instead of only maximizing its own profit. So this is a basic structure of a ride-hailing system. And in this field, there are so many papers. And now there is a review paper here that this review paper summarizes the current research in this area. They separate the research questions into 4 major types. One is the demand-related questions, like the demand estimation, as I just mentioned, and the pricing for passengers. And there are also some questions related to the supply side. For example, drivers' labor supplied and their relationship between the wage, the utilization, etc. And there is another stream of research focusing on the platform operations. For example, the matching between passengers and drivers, the vehicle relocations, the rating for drivers, etc. And the last category is about other aspects of the ride-hailing system. For example, the competition between the ride-hailing platforms, the impacts of ride-hailing platforms on other transportation systems like public transportation, and some government regulations that can affect the decisions of ride-hailing platforms. And in terms of methodology, there are different types of methodologies. Some economics theory like econometrics, labor economics, microeconomics, etc. There are also some operation management methodologies like queuing theories, optimization, dynamic programming. There are also some computer science methodologies like machine learning, deep learning, AI, etc. And different methodologies can be used to solve different problems. So if you have interest in this field, you can read this paper. So when we back to the Hong Kong market, in Hong Kong, Uber is illegal. Actually, it's illegal for drivers, but not for passengers. You can call Uber, and you have no risks. But the driver has a risk. If they are detected by the police, they will get punishment. But for passengers, you are safe. So the more popular mode in Hong Kong is the e-hailing taxi mode. That means you can use some apps to call taxis instead of private cars. And for these e-hailing taxi modes, actually their operations are the same or similar to the ride-hailing services using the private cars. So I would like to introduce a little bit about the Hong Kong taxi market. Now Hong Kong has a total of 18,000 taxis and around 40,000 taxi drivers. And as I just mentioned, nowadays the e-hailing taxi apps are becoming more and more popular, such as Uber Taxi, Hong Kong Taxi, and some other local taxi apps. So for the e-hailing taxi services, which is similar to the ride-hailing systems, they are quite complicated, and there are many dynamic evolutions of the states, the environmental states, like the passenger states, driver states, etc. And it is also a stochastic system. So when we want to maximize this system, if you use some static optimization algorithms, that would not be sufficient. So we can resort to the artificial intelligence, such as the reinforcement learning, which can learn from the real-time data to dynamically adjust their operating strategies so that we can make real-time decisions according to the real-time situations. However, when you are going to run some AI models, you need a testbed for trial and error, right? And even though we use non-AI optimization models, we still want to test different optimization models before we actually apply the best model into the real market. And here, this motivates our study about the simulation. That means we need to establish a test bed to train and test AI and traditional optimization algorithms to determine the pricing decisions, vehicle relocation decision, and even pricing decisions for ride-hailing platforms or e-hailing taxi platforms. And so this is the main component of my research. That is, we are going to establish a virtual taxi simulator that can describe the actual taxi system. And we will use the actual mobility data to calibrate the simulation platform. And after that, we can train and test different AI and optimization algorithms based on this simulator. And after we select the best one, we apply the best strategy into the real market. Then I will take some time to describe the simulation platform we have established. And then we will talk about some AI and optimization algorithms that can enhance the operations for taxi or ride-hailing services. So for this simulation platform, first, it is operating in real transportation networks. It can track the dynamic movements of vehicles very detailed in real time. And second, it has 4 major modules. One is the pricing module, one is the matching module, one is the repositioning module, one is the routing module. I will introduce them one by one. For the matching module, we consider different matching modes. For example, the broadcasting mode. So what is broadcasting mode? Broadcasting mode means when a platform receives the orders, they broadcast the orders to nearby drivers. And the drivers have freedom to pick up one order. They have the freedom to select the order or not. Right? This is broadcasting mode. This is widely used in e-hailing taxi app. For example, if you use Hong Kong Taxi or Uber Taxi, they use the broadcasting mode. Another mode is the dispatching mode. That means the platform directly assigns the drivers to pick up that passenger, and the drivers do not have the freedom to reject the assignment. So this is more widely used in ride-hailing apps based on private cars. For example, you go back to mainland China, you use Didi, the platform will dispatch a driver to you directly, and the driver cannot reject the assignment. And in our simulation platform, we can consider the algorithms for both the broadcasting mode and dispatching mode. And for the routing module means when the vehicle determines the origin and destination. For example, they are going to deliver one passenger to its destination. Then we need to determine a route for that vehicle. This is like the navigation app, like Baidu, Google, etc. So in our simulation platform, we also need such a navigation module. And here, for simplicity, we calculate the shortest path over the OpenStreetMap. And for the pricing module can determine in what case and in what situation the passengers are willing to pay the price. For example, when the price is higher, then some passengers may not be willing to pay the price. Right? So we can conduct some surveys to estimate passengers' willingness to pay based on different situations. So this is about pricing module. The last one is the repositioning module. That means when the drivers are idle, we want to simulate how these drivers randomly cruise on the street or strategically cruise on the street to find the next passenger. Or we can develop some optimization models that can tell the drivers how can you find the next passenger, how can you cruise on the street. So all the cruising behaviors belong to this repositioning module. So this is the details of this simulation platform. So here I will not go to the details. I just want to mention that this simulation platform is agent-based. That means each driver and each passenger is regarded as an agent, and each one has its own properties. For example, each passenger has its maximum allowable waiting time. When the waiting time exceeds this maximum waiting time, he will cancel his order. And every passenger has a willingness to pay. When you set the price higher than that price, then the passenger will cancel the order, etc. And for each driver, they have their status, whether they are occupied, they are idle, or their current location, their speed, they are matched passengers, there are online time and offline time, etc. So each agent has its property, and we will simulate the behaviors of each agent when we run this simulation. And for the data, when we establish a simulation platform, we need some data to calibrate it, right? Now we use some open source data sets. For example, the public data set for Uber, Lyft, and other ride-hailing companies in New York City. This is open source. And we also use some Didi data sets, which are also partially open to the researchers in Haikou and Chengdu. And we also have some private data set. For example, in Hong Kong, we have some taxi trajectory data set. This is a private data set, and we use this data set to calibrate the e-hailing taxi market in Hong Kong. And as I just mentioned, when we want to estimate passengers' sensitivity to price and waiting time, we will conduct some surveys. I will talk about the survey studies later. So this is a demo of our simulation platform. We have calibrated our simulation platform based on the open source data set in Manhattan, New York City. And here you can see that we can simulate the trajectory of vehicles in different status. For example, we use the red color to represent that they are delivering passengers, and we use green color to represent that they are on the way to pick up the passengers, and yellow color to represent that they are idle cruising on the street. And we also open source this simulation platform for the Manhattan, New York City. So if you have interest, you can check this GitHub website. And we also developed another simulation platform for Hong Kong. And this is for one project because we are required by the Transport Department in Hong Kong to establish a simulation platform for the e-hailing taxi market in Hong Kong. So we did this project for them. But unfortunately, this one is not open source because we have an agreement with the taxi company that we will not open source the data. And based on the Hong Kong data set, we conduct some experiments to check whether our simulated results are similar to the actual trajectory of taxis. And finally, we find that the error between the results simulated by our platform and the real trajectory data of taxis is around 12%, which means that our simulation platform can well simulate the real situations. And also, when we compare the driver's income, and we find that our simulated outcome is also similar to the statistics of driver's income. Because every year the government will publish some data showing the average income of taxi drivers. And after we run our simulation, we find that our simulated driver's average income is quite similar to the average monthly revenue published by the government. And as I just mentioned, we also conduct some surveys, right, to estimate passengers' willingness to pay and willingness to wait. And here we have distributed 1,000 questionnaires to ask the interviewees some questions. For example, what is your longest acceptable waiting time during the peak hours and off-peak hours? And what is the highest price you can accept, etc. Some questions like this. These are the questionnaire design. We ask some basic information, and then we ask what is the longest acceptable waiting time for your order, and what is the highest price you can accept, etc. And in different situations, we ask different questions. For example, during peak hours, in morning peak, evening peak, in non-peak hours, and these passengers may have different behaviors. And finally, we can summarize. We can find that their willingness to wait normally roughly follow a normal distribution. And then we can use this normal distribution into our simulation platform for the calibration. And this is the distribution for the pickup time. This is the distribution for the willingness to pay, the maximum price they can pay. And you can see that different passengers may have different maximum acceptable price. Next, let me take some time to introduce the AI and optimization algorithms for enhancing the taxi and ride-hailing services. So for the on-demand matching, for the matching between passengers and drivers, this problem is quite difficult. Why? First is the scalability of this problem. That means in a real time, we need to make this decision on very short notice. For example, if you match the passengers and drivers in every 2 seconds, that means you need to make the decisions within 2 seconds. So your algorithms should be very fast. The second is that when you make these decisions, you need to consider the spatial temporal varying demand and supply distributions, which means that they may affect your matching decisions. So when you make these decisions, you need to consider many factors. So next, I'm talking about for the broadcasting mode and for the dispatching mode, we have different algorithms for them. For the broadcasting mode, you see, for the broadcasting mode, we may need to make different decisions in real time. For example, the radius of the broadcasting. When you broadcast the orders to nearby drivers, then you need to set the radius, right? Within 3 kilometers, you broadcast the orders. And if those drivers do not accept, then you extend the radius to 5 kilometers, something like that. So the broadcasting radius is a very important decision variable in the broadcasting mode. Then we need to consider different factors. For example, driver's routing distance, if it accepts this order, and driver's service score, and some expected revenue of order. When the driver pick this order, how much can you earn from serving this order? So there are many factors that can affect the driver's decisions on picking up and selecting the orders. So when you determine the broadcasting radius, you need to consider multiple factors. So you can imagine that when the broadcasting radius is too small, then your drivers and your passengers may wait for a long time, right? But when your broadcasting radius is too large, then your order may be picked up by a very far away driver. And then the driver may spend a long time on the way to picking up this passenger. And this is a waste of resources. And we do not expect this phenomenon. So you need to make a trade-off between a large broadcasting radius and a small broadcasting radius. And then we conduct some experiments based on some criteria. We find that under different situations, the optimized broadcasting radius is different. For example, in some cases, the optimal broadcasting radius is 2 kilometers. In other cases, the optimal one is 5 kilometers. So you can imagine that the optimal broadcasting radius may change over time and over space. In different situations, different paces, different time intervals, you have different optimal matching radius. That means for different regions, we have different optimal matching radius. Then here, how many time I have? Okay. So let me finish this part quickly. So I will not go to the details. I just want to say that we developed a deep learning model that can help us to make decisions on the broadcasting radius. That's why we use the deep learning model, because we find that if we use deep learning models, we can discover more hidden patterns of the spatial, temporal, demand, supply, and situations. And so that can help us to make better decisions in the real time. So these are our algorithms. I will not go to the details. And finally, we find that if we run some simulations in Hong Kong and Manhattan, New York City, and we compare our deep learning models with some baselines, that based on some heuristics and some rules, and we find that our deep learning models can improve the system performance by dynamically adjusting the matching radius. And for the dispatching mode, we can also develop some AI models. For the dispatching mode, we do not need to consider too many factors, but we need to run a simulation, run an optimization in real time. For example, in the real time, you have a batch of passengers, a batch of drivers, and then you need to develop some algorithms, optimization algorithms, to pair those passengers with drivers, right? But when you run this optimization problem, it is myopic. What does it mean? It means that when you focus on the current spatial temporal demand supply distribution, and then you make the decisions, but you do not consider the current decisions will affect the future demand and supply conditions, right? After you do an optimization, you do a matching, then the environmental state will change. That means the supply and demand distribution will change. Using this figure, you can see that your matching strategy at time interval t-1 will affect the supply and demand distribution in time interval t. And that new supply and demand conditions will affect the future matching strategies. That's why your decisions and the environment are affecting each other. So if you just focus on one interval, you cannot get a very long-term maximum reward. That's why we need to use the reinforcement learning. Because when you run the reinforcement learning, you can try to optimize the system reward over a long horizon. For example, over 1 day. Then here we propose a framework that combines the online optimization and offline learning. In the online optimization, we still use an optimization algorithms, but here we not only focus on the instant reward we calculated from this batch of passengers and drivers, and we also focus on the future values of our decisions. And these future values are learned from some reinforcement learning. So in offline learning, our objective is to use some reinforcement learning to learn the future values. And after we learn the future values, in the online optimization, we do not need to train the reinforcement learning again. We just retrieve the future values from the functions generated by the reinforcement learning, which is already trained. So this can solve the problem of scalability and the algorithm efficiency. Why? Because in the online optimization, when you want to make decisions within 2 seconds, you do not need to train a very complicated AI models. You just use a well-trained AI models. And this AI models was trained in a simulation platform. So this is the idea for this one. And for the reinforcement learning, they have achieved great success in many fields. For example, playing chess, playing video games like the AlphaGo, and they are also successful in solving some transportation problems. And we prove that they are also efficient in dispatching the vehicles, matching passengers with drivers in our field. So this part too technical, so I skip this part. We just developed some reinforcement learning algorithms to help us to make decisions. And we can make different decisions. For example, for the matching, this is for the matching. And this is for the repositioning. That means we can move those vehicles from one location to other locations, from the cool zones to the hot zones. And then we can recommend some optimal cruising route for the idle drivers so that they can have higher probability to get the next order, and they can have higher expected income if they follow our suggested cruising route. And we also conduct some experiments. We compare some static optimization algorithms with our AI-based algorithms, and we find that our algorithms can improve the system performance, like improve the platform's revenue, the occupancy rate of vehicles, reduce the matching time of passengers, etc. And we can also extend these algorithms to do more tasks. For example, we can use it to coordinate the taxi services with the public transportation systems. For example, for each passenger, we can first recommend this passenger to use the taxis to reach a nearby metro station, and then use the metro station to reach his destination. So we can use similar algorithms to make route recommendations for the passengers. And in this case, we can find that if we use these algorithms, we find that when we combine the taxi systems with public transportation system, we can achieve a win-win situation. On one hand, we can increase the revenue of the taxi companies or ride-hailing companies. On the other hand, we can increase the usage of public transportation. So finally, let's look at the future research. As we have already established a simulation platform for taxi or ride-hailing services, in the future, we can extend it to multimodal transportation system to include other transportation modes. For example, buses, bike-sharing services, metro, and some flexible buses, etc. And because we have simulated the vehicle movements of all taxis, and also in the future, we can simulate the movements of buses, metros, etc. So we can use this aggregate multimodal simulation platform to estimate the carbon emissions of the transportation sector. Because we know the movements, trajectories of all vehicles, right? So we can estimate the carbon emissions. And we can also use it for the metro disruption management. We are now collaborating this project with MTR. MTR is interested in the disruption management. As you can see, there are many disruptions of MTRs. Sometimes there are some bad weathers, and sometimes there are some unexpected accidents, and then some stations will stop, right? So in this case, the MTR may need to dispatch some shuttle bus to satisfy those unmet passenger demand. And in this case, we can design some strategy to help them to arrange the shuttle buses by using our optimization and simulation algorithms. And we can also run the simulations for other transportation systems. For example, the meal delivery services, the last mile delivery services, etc. And there are similar problems for these scenarios. For example, for the meal delivery services, we want to dispatch the couriers to pick up and deliver meal orders. And we also want to dynamically adjust the price and wage for customers and drivers and even the merchants. So to summarize, in this study, we have established some simulation platform for shared mobility on demand, including ride-hailing services and e-hailing taxi services. And we have already developed some optimization and AI algorithms to enhance the service operation efficiency of these systems to solve some pricing problem, matching problem, and vehicle repositioning problems. And finally, the simulation platform can be extended to many other situations, such as the food delivery services, MTR, disruption management system, etc. These are the reference papers for this series of studies. Okay, thank you for your attention.